Hello, and welcome to this video, which should be first in a series, I hope, all about programming in assembly for the PCEngine or Turbografx 16 console. This first video, I think I'll just cover the basic hardware and capabilities of the PCEngine and Turbografx. I'll call it the PCE or PCEngine, and I'll get into assembly programming maybe in a later video. This will just be an introduction to the basic hardware. Hopefully you already know about and love this system like I do. Otherwise, why are you interested in programming for it? You should pick something that's more near and dear to your heart. The Turbografx and the NES, the Nintendo Entertainment System, are close to my heart, so that's why I wanted to start programming in assembly for them. The PCEngine runs off of a 6502 variant CPU, which means it's 8-bit. The CPU is 8 bits only. However, it does have some quite powerful, for the time, 16-bit graphics hardware. And that's where the Turbografx 16, the 16 in that name, that's where the 16 comes from, the 16-bit graphics. So the hardware, the CPU is only 8-bit, but it has to access the video hardware 16 bits at a time. So that's what you'll have to think about as you are programming for it in assembly. Usually every write you do to a register is always 16 bits wide. So it means 2 writes from the CPU. You can't get away from that. Anyway, you can see in my background, this is a picture of the PCEngine. The core graphics is right here, this little thing. And it takes little plastic cards as the game media, called Who cards or turbo chips. And in back is the CD-ROM unit. And running in this game, and in this PCEngine right now, is R-Type, as you can see right there, which made a big splash with its pretty reasonable facsimile of the arcade graphics for the time, which was 1987 or early 1988. So maybe I'll bring up a little block diagram of the PCEngine, the hardware. This green box here is what's inside the PCEngine itself. And to start with, when programming, I'll be sticking just to the PCEngine system itself, not to other parts of the system like the CD-ROM expansion interface. The CPU is 8 bits. It has a 16-bit address bus, and internally in the PCEngine it only has 8K of RAM, which is a little bit limiting compared to other systems. And the graphics hardware is called the VDC, or one of the chips is called the VDC, the Video Display Controller, and that has 64K of video RAM built in. And the CPU can read from and write to the video RAM, but it can't use it as its own program RAM. There are the expansions like the CD-ROM unit, which came later, added 64K of work RAM, which stored the game program, as well as 2K of backup RAM for game saves, and another 64K of RAM for ADPCM samples. So it had its own hardware sample player built into the CD interface. But the CPU could not address the sample RAM directly. It had to read and write through ports very slowly. Anyway, the CD player and the sample RAM was channeled out the audio out through the CD hardware. As well as the CD-ROM unit, it came with the system card, a CD system card, which had 256K of ROM for the system software, the CD system software. And that was basically it for several years. 64K of RAM to store the whole game, and then you'd have to load more off CD. In 1991, the Super System card came out, which added 192K of work RAM to the CD unit, and so it made for a total of 256K of RAM, or 2 megabits at the time. Not gigantic, but it was a bit of a relief. Most Who cards, which were running on this external media, they were 1 megabit or 2 megabits, 3 megabits, 4 megabits, and then later on they became 6 or 8 megabits, and Street Fighter 2 was a special one at 20 megabits. But if we're going to do programming, we're going to stick to the card format for now, and then maybe do CD-ROM programming in a bit. All right. Maybe I'll start with a quick little crib sheet for the CPU registers and instructions. I have two really nice pictures called Otaku no PCE crib sheet made by Tomathius, and this has all of the let's see, full zoom. It has all of the instructions and their flags for the CPU, as well as memory map for the system. All right. So the CPU is called the 6280, HUC 6280. That's Who for Hudson Soft, because they were the people who developed this hardware. It is very much like the 6502. You have an 8-bit accumulator, X register, Y register, a stack pointer, the processor flags, program counter. It also has the vectors that it needs to start up. They should be in ROM. Just like the 6502, it has a reset vector, NMI vector, and IRQ vector, all at FFF something in program ROM. So here are the 6280 registers, vectors. At FFFE, it's reset. FFFC, it's NMI. FFFA, there's a timer. There's a built-in timer in the CPU. VDC, the video interrupt, and then break, IRQ2. And here is a typical memory map for a game. The 8K of RAM is banked in at the 6502 address 2000 all the way up to 3FFF, and then from 4000 and up it's various different other things. It could be ROM, could be other types of RAM, could be I/O. Usually hardware I/O is mapped in at address 0000, and most port addresses are at 000 something or 1000 something, which I'll get into later. Okay, so now I'm in a room with a bit less reverb and a bit less noise. I'll continue. I'll show maybe a PC Engine game and explain what you see and how the CPU and VDC is working. So I'll start one up. Here we go. This is the emulator Mednafen with the familiar Kung Fu or China Warrior game. I think this is like the first game that ever was worked on the PC Engine. Actually, I think it's Hudson Volume 1. So anyway, start it up. Well, it's not a great game, but it has good music. But anyway, it's famous for giant sprites, of course, and that's was the selling point of the PC Engine and Turbo back in the day, compared to the NES, and even compared to the Genesis. It had larger sprites, so that was quite a major selling point. Back when large things on screen were really difficult to do. So I have the emulator paused right here. If you do Control 1 and Control 2, you can turn on and off the background or the sprites, so you can see what each side of the VDC is doing. The PC Engine has a single background layer, and so only one layer is here. It scrolls in parallax by doing a screen split, a raster split, just sliding various portions of the single background at various different speeds. So it doesn't have two layers of background like the Mega Drive does, or more like the Super Famicom does. It has a single background layer, so it's very similar to the NES in that regard. But the sizes can get much larger. The size of the background and the number of tiles it can address is much greater. So if you press Alt D in Mednafen, you bring up the debugger, where you can view the CPU running and trigger breakpoints and view VRAM and other RAM portions and stuff. So here you can see it's running and just cycling on a portion of memory. I'll press S to single step the debugger, and that's how you single step. Right now, as you can see, it's loading value from RAM, and RAM is from 2000 hex up to 3FFF, and it's checking if some flag is set and then branching back. So obviously it's waiting for some kind of interrupt trigger so it can continue. Over here on this side you can see the CPU registers, and so the program counter, A register, X, Y index registers, stack pointer, well, flags, processor flags, and here are the MPR registers, the memory paging registers, and speed flag. So the PCEngine CPU can run at two different speeds. Slow speed, which is what it starts up upon reset. Slow meaning 1 point something megahertz, and so you need an instruction to actually switch it into high speed mode, which is 7.1 something, 7.14 megahertz. So of course, if the flag is set to 1, that means it's in high speed mode. And then some timer and IRQ flags and countdown timers. Over here is the VDC's internal registers, so the screen dimension settings and memory write, VRAM write, VRAM read registers. And over here are the audio registers. And so the PCEngine has 6 audio channels. They're similar to PSG, like the NES, in that they play primitive waveforms. However, you can set the waveform to anything you want, basically, but it's limited to 32 bytes of one single loop of an audio waveform in memory. And so you can set it to primitive waveforms like a triangle wave or sawtooth wave or pulse wave or square wave. You can do that freely, but still it's limited to 32 bytes of waveform memory per channel. That means 32 different levels to define one loop of a sample. And so the last two channels, this one and this one, channel 4 and 5, can be switched into noise generation, like white noise generation, and it's very similar to the NES. It's got a volume and 16-step noise frequency control. And channel 1 can actually modulate channel 0, which means it has a low frequency oscillator. It doesn't really do FM, but it can give vibrato effects or things like that. And yeah, that's basically it. Most games set maybe 1 or 2 channels at the end to noise for percussion, and maybe well, a lot of games set 1 channel to produce direct samples, because you can set any one of the 6 or all of the 6 samples to direct DAC output to pump samples through. But of course that takes up a lot of CPU resources, because you have to do it all through using the CPU. There is no automatic sample playing. So most games just set 1 one channel to direct sample output, and it sets a timer to pump that through at high speeds. But it does consume the CPU and ROM space resources. And then the rest of the channels are set to regular waveform or PSG, WSG style. So anyway, what else you can see? You can see, I guess this is the stack history of the jumps in the program space. And here's 0 page in a map. So, well, I get to memory then. I probably said before a little bit, the PCEngine can bank in and out different memory spaces into its 6280 memory space. So it's got a regular 16-bit addressing space, just like the 6502, but you can bank in and out different regions of ROM or RAM using these 8 memory paging registers. 0 sets, of course, address 0000 to 1FFF hex. That's the first 8K, and then 2000 to 3FFF hex is the second memory MPR region. And so, well, FF right here is the I/O ports, the I/O registers. So registers are mapped in at 0000 or 1000 hex, and then RAM is mapped in at 2000 hex to 3FFF. So F8 right here is PCEngine's 8K of RAM. That's the bank that it's in. And then bank 0 is the ROM. It's the first 8K of ROM, and that's always set at default, so that the game starts up in bank 0 with the reset vector pointing to somewhere in that 8K of space. And then the game can page in its own ROM regions. So you can see here the game pages in its own bank 1, 2, 3, and then 4 and 5 here. And then it sets the RAM and I/O ports as well. And so, well, let me show some. Let me hit reset. Actually, I'll do F11. Press F11, and that resets the game. And so you can see the instructions right here. First of all, the memory is everything is cleared. The program counter is set to E000. Well, not automatically, but first of all, ROM bank 0 is mapped into MPR7, and that the vectors obviously jump it right over to E000 to reset. So E00 is at the reset vector. Sets the interrupt disable flag first. Sets the CPU to high speed mode, CSH. Clears the decimal mode. And then you can see here it will load in value FF and bank that in to MPR1. That's TAM, transfer accumulator to MPR register. 01 is bitwise, so it does 1, 2, 4, 8. So MPR0 is TAM01, MPR1 is TAM02, MPR2 is TAM04, and so that's the bitwise value that you define in the TAM instruction. So load A with FF, transfer that into here, boom. So that just maps in the I/O ports, so you can actually write all the I/O. Then you see here it loads F8 in and transfer that into O2, TAM02, that'll bank it into memory paging register 1. There, so now RAM is active, RAM is available, so the game won't crash if it tries to write to RAM or read from RAM. And so here it sets some flags and sets the 0 page with memory, as well with its own variables. Yeah, and then clears memory a little bit. Alright, I'll jump down here. I hit space to actually set a breakpoint further along, and then if I hit R, that'll run to the breakpoint. Boom, right there. And then I can hit space again to turn off that breakpoint. So after clearing some amount of RAM from 3,400 to 4,000, I guess it leaves the lower parts for a while. It'll clear the interrupt again and set high-speed mode again, just to be safe. I guess that's the basic boilerplate routines in the game. Set high-speed mode again. Here we load X with FF and transfer that to the stack pointer. So this is a standard initialization in 6502. And so the stack pointer will be finally initialized to FF. Okay, I'll stop here. Just like 6502, 0 page is the first 100 bytes of RAM. First hex 100 bytes of RAM, and then the stack is the second hex 100 bytes of RAM. But RAM is actually starting at 2000 hex in the 6502 or 6280 address space. So what's going on with that? Well, 0 page is always hardwired, I believe, to 2000 hex in RAM. So even if you map your RAM somewhere else, you kind of need to have RAM still in MPR1, just so that 0 page writes point there. And the stack is the same thing. You always have to have RAM mapped in to MPR1, because that's where stack accesses always happen. So actually I'll show what that is now. If you do Alt-3, you can view hex dumps of the various RAM spaces in the PC Engine. So CPU logical is basically what this 6280 would see. Is what 6502 would see as well. It's only 16 bits, so 000 is, well, it looks like garbage because that's basically maybe write-only or some read-only I/O ports, some registers. So there's nothing special to see here. If you hit G, you can go to another address. So I'll go to 1000. That's some different I/O ports, I/O addresses. 2000 is where RAM starts, and you can see here the first 2 bytes was the count up address for writing to RAM, and then 2100 is, well, it's still RAM, but 21FF is now what the stack pointer is set to, right here. And it goes all the way up to 4000, or 3FFF hex. And so that's the end of RAM, that's 8K of RAM. And then at 4000, well, it's 78D48, that's of course 6502 code. So at 4000, what's there? Well, nothing really, it's still initialized to 00, so that's the ROM. This is the first 8K of ROM, so there's nothing initialized there right now. So I'll let the game run and you can watch it set up the memory paging registers to things that it needs for the game. Yeah, 1C05. So yeah, this usually changes, so that's probably where it's getting its graphics from. Oh, sorry. Start that up. Hello. I'll hit S to stop the disassembly. Alright, and let's see. Well, the game is frozen right now. I will hit Alt-2 while in the debugger, and that brings up the VRAM viewer. So this is where you can see the 64K of VRAM as tile memory. This is as a background tile, and this is as a sprite tile. Unfortunately, the PC Engine has a different graphics format for backgrounds and tiles. That's kind of too bad. On the NES, I think on the Super Nintendo as well, you can use the same graphics tiles as either a background or as a sprite. But on the PC Engine, they're a totally different format. Or they're a little bit different format. The background uses 8x8, 4 bits per pixel tiles, and the sprites use 16x16, 4-bit per pixel tiles. Alright, anyway, the first, well, whatever K of memory, this would be the first, I'm guessing that's 2K of memory here, is set as the background map. You can set that to various sizes, either 32 by 32 tiles or 32 by 64. I think it can go up even to 128 by 64, so quite a wide or a large background map, and so the size of that changes depending on what you need to use in your game. So this is not graphics, this is the background map with the definitions for all the tiles. And right here you can see the sprite attribute table. So if you see a bunch of junk right at the start or in the middle or right at the end of VRAM, probably that's the sprite attribute table. The PC Engine usually stores sprite attributes in RAM in the CPU first, and then the game program will actually transfer that, usually through a block transfer, into VRAM, and here it is in VRAM, and then the game has to ask the VDC to transfer that automatically every frame into its own sprite attribute RAM. So it's kind of like a 2-step transfer, whereas on the NES it was only like a 1-step DMA transfer. But oh well, whatever. So you can scroll down and see the background tiles, and these are the ground, the mountains in the background, the clouds, and then this looks totally different because this is obviously sprites. The game uses giant sprites, so most of the VRAM is taken up by sprite graphics. Yeah, definitely. Oh, there's some more hidden things, hidden or unused graphics back here. All right. So I'm hitting comma or period on the keyboard to change between one of the 16 different background palettes. And the PC Engine has 15 background palettes and 16 background palettes and 16 sprite palettes. So that means 32 palettes of 16 colors each. That's up to 512 colors. It's kind of a maximum of 482 colors on screen at once, which is actually more than either the Super Famicom, Super Nintendo, or the Mega Drive, without resorting to timing or other kind of transparency effects. So anyway, this looks like it's unused graphics here. Kind of interesting. Anyway, if you hit right arrow, you go to Sprites, and you can look at that. So nothing really special here. This is still background graphics. And here is where the sprites begin. This is our Bruce Lee wannabe. And some minor enemies. Where's their palette? There it is. So a dragon or a snake or whatever, and some enemies. Then some explosions right there. So as you can see, video RAM is laid out tile by tile, and then definitions for sprite tiles or background tiles are then written into sprite memory or into the background map over here. So if I hit Alt-3, I go back to this hex viewer, and if you again hit period or comma, you can scroll through the different types of address space. So this is CPU logical, this is CPU physical. As you can see, it's much larger. It goes up to 1F, FFFF, and of course everything's all 0 means bank 0, that's where the ROM starts, and bank FF is where the IO ports are, and RAM is F8. Usually you don't need to do that, you just set it once at the start, and then you bank in and out your ROM spaces. So you just need to remember when you're programming where everything is in ROM. Here's RAM. Again, it's only 8K, so it goes up to 1FFF in hex. And here's the palette RAM, the VCE palette RAM. Well, it goes up to 400 hex. There's 200 hex bytes for the background palette, and then 200 hex bytes for the sprite palettes. The palette RAM is, or each color is defined by 2 bytes, but it's 9 bits, so it's 3 bits each for red, green, and blue. Not much, not a lot compared to the Super Famicom, but still, well, it's on par with the Mega Drive, more or less. I wish the PC Engine had a wider color space, but that's what you got back in 1987. And here's VRAM. You can view VRAM as, of course, hex bytes. Now remember, the VDC treats everything as a 16-bit value. It addresses everything in 16 bits. So whenever you write to VRAM, it's always 2 bytes at a time, and the address definition that you write to the VDC is going to be half in value of what you actually are thinking about in terms of bytes. So even though there are 64K bytes here, so that goes up to FFFF, really inside the VDC it goes up to address 3FFF. I'm sorry, my mistake, 7FFF. So basically you cut this byte value in half to get the word value of the address that you're writing to in the VDC. It's a little bit tricky. The PC Engine CPU is only 8-bit, but you have to think in 16 bits some of the time. Here's a sprite address or attribute table. BRAM, backup RAM. We don't really use that here. The game certainly doesn't use it here. And then finally here is the PSG RAM for each of the sample channels. It's only 32 bytes, so it's 5 bits of wave data for each byte. It's not very high definition samples, and so usually you got 32 bytes to write 1 loop of a sample. So here's a pulse wave. It's an elongated square wave with a different duty cycle. This looks like an organ sound. It obviously dips down and then wraps around and then goes down and then comes up again. So it's a large sine wave that wraps over twice, which introduces some noise, but that is kind of the low bit quality of the PC Engine. Square waves. Here's a sawtooth wave. You can see it goes down immediately and then ramps back up and then goes down. So it's only one period or one cycle of a waveform. Here's the same thing again, and so here's a triangle wave with a little bit of noise at the start. So it's obviously like a little bit noisy triangle wave. And that's it. So I'll quit this and maybe quickly show a couple other games or graphic demonstrations. Well, I'll start up PCEngine-2. That's Bonk's Revenge. Oh, that's quite beautiful. Let's see how it organizes its VRAM. So again, background layer, this is uninitialized. Probably this is Sprites right here. So standard font definitions, Sprites. Here's the game background, or the title screen background. Everything's tile-based. So there are ways to import your own, canvases from a paint program into the PC Engine, but generally a lot of people, programmers, arrange things as tiles that they will reuse over and over for their whole map. And there are some programs that make a more efficient map out of your graphics. That's basically it. Nothing too interesting here. Sprites. Yeah, okay, here we go. A cloud, PCEngine. Maybe I should run the game a bit more. Run. Let's wait till the 2 fades in. There we go, that's better. So the game obviously loaded in a missile graphic and the egghead, the Chikun character, and here's Bonk, PCEngine. There he is. And a bunch of flame. Yeah, so that's basically it. Nothing really special to look at. Alright, I'll show very quickly what you'll see on screen, or what you're able to put on screen. Here's a quick 512 colored test demo. Basically, these are all the colors you can work with on the PC Engine. You've got 8 shades of gray, you've got 8 shades of red and green and blue, and the combinations thereof. There are limits to where you can put colors. So, as I said, tile graphics and sprite graphics are each 4 bits per pixel only. So you can only put 16 colors from this large palette into one little tile. And so games got around this by, of course, using 16 of those palettes and arranging them in intelligent ways. So you can't just have VGA quality graphics with any of the 256 or 512 colors anywhere you want all over the screen. You're going to have to be clever and rearrange them, or else you'll get color clash or attribute clash, or the game will refuse to assemble if you have too many colors of different palettes next to each other. It's the same as on the NES or Commodore 64 ZX Spectrum. If you grew up with the ZX Spectrum, you know color attribute clash. So same thing here, except instead of attribute clash because of more than 2 colors next to each other, this is if you have more than 16 colors of the same palette next to each other. So I made this show all the colors on screen at once by having a horizontal interrupt trigger every 8 lines, and then rewrite the palette every 8 lines. And you can actually see that here if I change the where the interrupt splits. So sometimes if you want to get great graphics or really colorful graphics on the screen, you either have to be really artistic or clever with your programming. Next we'll get to the screen dimensions, the screen size of the PC Engine. Well, I'm running this in a little window in an emulator, so you can't get everything here, but basically the PC Engine has 3 different horizontal resolutions. It has the standard, quote-unquote, 256 pixels wide. It has a 320 pixel wide mode, although if you get the same width, if you want the same width as the 256 pixel wide mode, actually it's 352 pixels, so it's pretty wide. And then finally it has a high resolution mode, 512 pixels, as you can see here. So you can get your standard NES style graphics like this. It's 256 pixels wide and up to 241 pixels tall. So, and you can adjust these parameters yourself as a programmer. If you change the vertical start position, you can make the screen smaller, narrower, or really you can make it really tall as well. You can see at the bottom of the screen I'm making the screen shorter or taller. And I made this program just so you can test out the screen dimensions on your TV or in an emulator. As you can see here, this is the 320 mode, but really to get the same width as this, the 256 pixels, it's around 352 pixels now. So you can get nice wide, still medium resolution screens in the PC Engine, and this is what R-Type uses. A lot of IREM games use this mode because it's the same as their arcade games. Really wide graphics, and you can make them even wider as well. 370 something odd pixels. It depends on the limitations of your TV, but most modern LCD TVs actually show a really large area of overscan and can auto-adjust, so it's maybe even more than tube TVs. And again, 512 pixel wide mode, you can make it even larger. And so there I have it at, geez, how much is that? 560 pixels wide. So if you wanted to get detailed graphics, you can. Generally, there's enough VRAM to have a single 512 by 240 wide screen with all pixels individually, or with all pixels distinct, so no repetitions. So you can have a pretty large canvas, but then your VRAM is maxed out. But still, it's good for title screens, or if you want to have a high-resolution Mandelbrot, you can do that too. All right. Okay, and I think that's where I'm going to end this video for now. In another video, I will talk about how you can make audio. Although it's not my forte, I'm not a musician, I got no idea how to actually write music, but there are some programs that let you make audio, make music. But maybe in another video I'll talk about the basic limitations and registers and things like that for the audio channels on the PC Engine. But for now, that's the end of this first video. Tell me if you like it.